Dear students, today we will start the topic the motion in the presence of a cylinder. Motion in the presence of a cylinder. First of all, we know that if you have some function, say w, which is a function of z, where z is defined in the complex plane, then if the derivative of w, that means variation in w, is allowed. It simply means that if I write w to be phi plus I psi, then it simply means that if this variation is allowed, then phi as well as psi will satisfy Laplace equations. That is, delta 2 phi is 0 as well as delta 2 psi is 0. Or we may say that without any loss of generality, phi will be the potential function. Potential function or the function for the potential flow. And if phi exists, then Cauchy-Riemann equation says that psi will also exist, and it is called psi also exists and is called stream function. So there may exist complex velocity in the form dw dz, and which I told you earlier may be written as minus u plus iv, where dw dz will give you the resultant of the velocity, that means u square plus v square. When I started the complex variable technique, then I told you everything about this, that how by using this w we can solve our flow problems. The same technique will be used in studying the motion in the presence of cylinder, in which we will define a w, and then we will find what are the streamlines, what are the potential lines, what will be the velocity, what are the stagnation points, or what are the forces present in the flow or forces acting on the cylinder. So what we do, first of all, as you seen earlier, we have taken a w, we have defined a w. There are two ways: either you have phi and psi, you define a w with the help of phi and psi, and then you analyze all the things related to flow, or the second way is that you assume some w according to the flow situation. For example, I am taking a type of flow. As you are discussing about the motion of fluid in the presence of cylinder, I tell you that we'll discuss some cases in which the first case is when cylinder is moving rectilinearly. It simply means it may move either in x direction or in y direction. The second situation is when cylinder is at rest and fluid is moving rectilinearly. But in this case, we will assume the fluid to move in the same direction as the cylinder was moving, only the direction will be opposite. That I'll explain later. And the third situation, when cylinder is at rest, that means cylinder is fixed, but fluid is moving rectilinearly as well as circulating around the cylinder. Okay, so these are the three situations. So as I told you that there is the way that you know phi, you know psi, you define W, and the second way is you assume W according to the situation, or you assume phi according to your situation. For example, I am handling the first problem and I will tell you that how we can assume W for it or assume phi, and I'll explain the method to find the W or the complex potential in two ways. So first of all, I am considering this case. Cylinder is moving rectilinearly. So case 1. Cylinder is moving rectilinearly. That means I am considering cylinder is moving rectilinearly. I assume that it is moving rectilinearly in positive x direction. Clear? So suppose this is your cylinder. Consider a cylinder of unit depth. This we do to simplify our calculation of unit depth and radius A. So this is the cylinder and this is the flow region. Your cylinder is moving with velocity u in x direction. So at any point of the cylinder, if I draw this line and this angle is theta, then at this point I may draw two lines like this, where this is the horizontal component of velocity and this is the vertical component of velocity. Similarly, this will be QR because it is along the radius. And if I am taking along the tangent, this will be Q theta. So if I talk about QR, this angle is also theta. What will be QR? QR is equal to, this is QR. QR is equal to, because you have one component of velocity u in x direction, so it will be u cos theta. Now this QR may be written as, this is QR. This QR may be written as minus delta phi delta r. So it is u cos theta. You may say it is at the cylinder, though it is free from r. So it is at the surface of the cylinder. Now in this case, it is assumed, this is first point, now it is assumed that the fluid is at rest at infinity. You can assume it without any loss of generality, because when the cylinder is moving, the fluid which is in the neighbor of the cylinder or which is adjacent to the cylinder will also move with some relative velocity, while the fluid which is at a distance from this cylinder will be at rest. So we may assume that the fluid is at rest at infinity. This implies QR, radial component of velocity, as well as transverse component of velocity, both will be 0 at r is equal to infinity. Now, if I look at this condition, if I look at this QR, and if my delta phi delta r is like this, I may assume a form of phi. Like what I will assume? I assume that the most suitable solution for phi will be AR plus B upon R cos theta. On the previous page I should give it 1, this is 2, and now this is 3. So we have found earlier that at r is equal to a, that means at the radius, at the surface of the cylinder, phi was delta phi delta r was just a minute. I found delta phi delta r to be u cos theta minus u cos theta. So it is minus u cos theta. So from 3, a minus b upon r square cos theta is minus u cos theta. Or if I compare, then u is equal to minus a minus b upon r square. Now what is u at r is equal to infinity? U is equal to 0. So this implies 5 implies that a is also 0. And so b is equal to u r square. Now at r is equal to a, what will be b? B is equal to u a square. So finally you got the value of a and the value of b. So put these values in 3 and you get phi. 3 implies phi is equal to a0, b is u a square upon r cos theta. So in this way you get your phi. Similarly, with the relation between phi and psi, which is delta psi delta r is equal to minus 1 upon r delta phi delta theta. Use this value 6 and get minus 1 upon r minus u a square upon r sin theta, that is u a square upon r square sin theta. So this is the value of delta psi delta r, and integrating you may get your psi. Psi will be minus u a square upon r sin theta. So you got phi, you got psi. In this way I can very well write what will be the complex potential, which is our main aim. So complex potential W will be phi plus I psi. Now put the values. Phi is u a square upon r cos theta, and psi is minus u a square upon r sin theta. You may write it as u a square upon r cos theta minus I sin theta, which is nothing but u a square e raised to the power minus I theta r u a square upon r e raised to the power I theta, that is u a square upon z. So this is the way in which you can find your W. W is complex potential. You have learned about it in sources, sinks and doublets, that how we find phi, how we find psi, and then how we create our W. Now I would also like to tell you the another way of defining, which is quite simpler. The rest of this I'll do later after this. This is the second method to find W. Since fluid is at rest at infinity, so I assume W to be B upon Z. This is just a hit and trial method, because I get dW dZ is minus B upon Z square, and as dW dZ is 0 at Z is equal to infinity, so it is satisfied. And since it is satisfying the condition, so we may assume B to be of this form. Now phi plus I psi will be from 1 B upon r cos theta minus I sin theta. This implies phi to be B upon r cos theta and psi to be minus B upon r sin theta. So what will be our QR? Phi means I can get QR minus delta phi delta r, and it will be minus B cos theta upon r square. Now what was QR at r is equal to a? It was u cos theta, and now this will be minus B cos theta upon, at r is equal to a, it will be a square. So what is our B? B is equal to minus u a square. It is minus u cos theta. So comparing, B is equal to u a square. Now put the value of B in 1. So 1 implies W is equal to u a square upon z. you look at this, both are one and the same thing. So this, in this way also, you may start your article by assuming W to be of this form. So now we proceed for other things of this article. We get W to be U A square upon Z, and other expressions were QR was 0, no, QR was U cos theta at the cylinder, and we can calculate Q theta as well. Phi was U A square upon R cos theta, and psi was minus U A square upon R sin theta. So with the help of phi or psi, you can very well calculate your Q theta. What is QR? QR is the radial component of velocity, and what is Q theta? It is the transverse component of velocity. So first of all, if you have to find what is streamlines or potential lines, so I am calculating the streamlines. In some questions it is very easy to draw the streamlines, while in some other questions it is difficult to draw the streamlines without doing the whole calculation. So in this case we can easily recognize the streamlines even from the mathematical expressions. Otherwise we will draw the streamlines with the help of stagnation points. So streamlines will be when psi is equal to constant. It means U A square upon R sin theta is constant. I take it to be minus U A square. You may ignore this minus also with the help of this constant. You may take U A square R sin theta upon R square is equal to, let it be C1. So U A square upon C1, the C1, take this C1 in the denominator. R sin theta means y, and take this R square here, it is x square plus y square, or x square plus y square minus take it to be C2, y is equal to 0. If I take this constant to be negative, then I will get like this. If I take this constant to be positive, I will get this with plus symbol. So solving this, you can easily recognize it. It is the equation of a circle. I get x square plus y minus C2 whole square. I may take it twice C2 as well, where what is twice C2? Twice C2 is U A square upon C1 is equal to C2 square. So it is a circle with center 0 C2 and radius C2. As I told you earlier, the center of the circle may be 0 minus C2 as well. So either you take 0 C2 or you take 0 minus C2, one and the same thing. So it is representing circle. It was 8. So now you are at 9. This is 9. Similarly, if I talk about the potential lines, so I may very well calculate the potential lines. these will be phi is equal to constant. It is u a square upon r cos theta is equal to constant. So proceeding in the same way, multiply and divide by r constant, you may get it is u a square, r cos theta is x, is equal to x square plus y square upon constant, let it be c3. Then take u a square upon c3 to be twice c4. You will get x square plus y square minus twice c4 x0, which is representing another circle c of x minus c4 square plus y square is equal to c4 square. So it is a circle with center c40 and radius c1. So these are potential lines and these are streamlines. Now we will see what will be the velocity. To calculate velocity, you may use any of the approach which I told you earlier. Here I am taking minus u plus iv is equal to dw dz, and dw dz is equal to u square plus v square. dw dz is I can calculate it from the expression of w. dw dz is minus u a square upon z square, or u can be taken outside, a square can be taken outside. I am taking modulus on u, though I have taken u to be in positive x direction, so u may be taken as positive itself, and then in place of z square I'll put 1 upon r square cos 2 theta minus I sin 2 theta, and calculating I get it u a square upon, this is z square, this is r square, so it is take it at r is equal to a. You can take r to be outside at r is equal to a, and this will give you 1. So what is it? It is modulus of u. And you see it is independent of theta. It simply means that this is dw dz modulus of u. So what is the stagnation point? Can you calculate the stagnation point? No, because it is a constant velocity. So there is no stagnation point. Rather, what is the maximum velocity? It is positive u. This is the maximum velocity. So in this case, this is your maximum velocity. There is no stagnation point. Further, you can calculate the pressure. You can calculate pressure. Pressure may again be calculated with the help of integration of the force. That means force. You can calculate force with the help of integration or directly by the Bernoulli's equation. For example, here pressure plus half rho q square is equal to constant. So if I say that at r is equal to infinity, p is pi, say p is pi, and what is q at infinity? Q is 0. So I get the value of the constant to be, constant is equal to pi. So I put here in this constant, A implies P is equal to pi minus half of rho Q square. I may put the value of Q square. It is pi minus half of rho U Q square. So it is U square A4 upon R4. If I want to find what is the pressure at the surface of the cylinder, so at the surface, put R is equal to A. I put R is equal to A and get pressure to be pi minus half rho U square. Now here we can discuss an important point, that how will we prevent the cavitation. Actually, if this is a cylinder and this is the direction of the pressure, so it is necessary to prevent cavitation that this contact should be there, and this contact will be there if P is positive, because in inward direction P is taken as positive. So to prevent cavitation, this should be greater than 0 to prevent cavitation. Otherwise, what will happen if P is not greater than 0 or P is not in this direction? There will be a gap between the cylinder and the fluid, or you may say that fluid will leave the cylinder and there is a possibility of cavitation. So what should be U to prevent cavitation? That pi should be greater than half of rho U square, or you can say that U square should be less than twice pi upon rho. This is the condition to prevent cavitation. So this is about the pressure. Similarly, you may calculate the kinetic energy. We have defined in Green's theorem that kinetic energy is rho by 2 phi delta S ds. Where what is this delta phi delta S? Delta phi delta S is, in actual delta phi delta S means delta phi delta N. That is, it is the velocity in the direction of normal. So it will be half of rho phi of delta phi delta R, because what is delta phi delta N? This is delta phi delta N. So this is the radial velocity. This is equivalent to QR, and QR is delta phi delta R. And what is ds? This is delta S. So what is ds will be replaced by rd theta, where theta goes from 0 to 2 pi. So now we put the values. Rho by 2, 0 to 2 pi, phi is u a square upon r cos theta. Delta phi delta r is minus u cos theta r d theta. As we want to find what is kinetic energy at the surface of the cylinder, I put r is equal to a. So I put r is equal to a, I put r is equal to a, and this will be cancelled with this term, and we are left with minus rho by 2. U square is constant, so take it outside. A square will be cancelled. Integral 0 to 2 pi cos square theta a square, this a square d theta, and solving it you will get minus rho by 2 u square a square 0 to 2 pi. You take 4, so it is 2 cos square theta cos 2 theta plus 1 d theta minus rho by 4 u square a square sin 2 theta upon 2 plus theta 0 to 2 pi. So it is nothing but minus rho by 4 u square a square into 2 pi so it is minus rho u square a square pi upon 2. This is all about kinetic energy. Similarly, here the minus symbol will not affect the quantitative result. It will just tell you the direction. You can also write it as half of m dash u square, where what is this m dash? M dash is equal to rho pi a square. What is this? Pi a square is the area of the cross section of the cylinder. So when rho is multiplied by area of the cross section of the cylinder, it becomes mass of the liquid displaced by the cylinder. It is mass of the liquid displaced by the cylinder. M dash is mass of the liquid displaced by the cylinder, as it is the cross sectional area of cylinder and this is the mass of the liquid. So multiplying the two you will get the total mass which is displaced by the cylinder. So it is all about kinetic energy, and in this way you have calculated the kinetic energy, the force, the velocity potential, the stream function, the stream lines and maximum velocity, and the nature of the stagnation point if it exists. So it is all about this article. Next we will see the next case in the next lecture.